This is the second part of lecture 5 of modern construction materials. We have looked at different ways that microstructure forms in solids. We started discussing phase diagrams, and now we will go on to see binary phase diagrams and have a short discussion at the end on sintering. Now, we looked at the Gibbs phase rule when we started the discussion on phase diagrams. When we have a binary phase diagrams drawn for two component systems, we have these diagrams at atmospheric pressure with temperature and the composition as the variables. That is, the Gibbs phase rule becomes F plus P equals to n plus 1. Also, we find that in binary phase diagrams, a two phase region always separates a single phase region from another single phase region. That is, between two single phase regions, there will be a region where two phases coexist. This is called the 1-2-1 rule. So, let us take this binary phase diagram. It is a hypothetical phase diagram between two elements A and B, element A and element B. We assume that these elements have complete liquid and solid solubility, that is, in both the liquid form and solid form they are completely soluble in each other, and the solubility is in all proportions both in liquid and solid state. F plus P becomes 3 in the Gibbs phase rule. We have this part which corresponds to the liquid phase, and this part corresponds to the solid phase, and we call it here alpha. So, this is the alpha solid phase, and as I said before, between different regions with single phases, there will be a two phase region separating them. So, this is the dark blue region where you have the alpha solid phase and also the liquid phase. Then we find that within this region two phases have to coexist, that is, P is equal to 2. So, according to the Gibbs phase rule, F becomes 1. Within this region there is only one degree of freedom, that is, if we change the temperature, there is always a corresponding composition. That means that there is a line which fixes the composition for each temperature. This is called the tie line. Cl, that is the composition corresponding to the edge of the tie line, gives the composition of the liquid. The other edge bordering the alpha phase region, that is the solid phase region, Cs is the composition at the point where the tie line meets the border between these two regions, gives the composition of the solid phase. So, at this temperature within this region, the composition of the liquid phase is given by Cl and the solid phase is given by Cs. Also, we find that in multi-component systems, the melting of the material occurs over a range of temperatures. It is not at a fixed melting point, but the melting occurs over a range of temperatures. Between the solidus line, this is the solidus line separating the region of the solid phase alpha and the two phase region alpha plus L. Similarly, we have a liquidus line which is the upper bound of this region. separating the region where we have the liquid phase and the region where we have the alpha plus L phase, that is the solid phase and the liquid phase coexisting. So, this is the liquidus line, and what we find is melting occurs over the region between the liquidus line and the solidus line. Within this temperature range, the solid and liquid phases are in equilibrium. We can show this diagrammatically with these 3 diagrams. Here you have the liquid solution, you have a single liquid phase shown here. Now, as the temperature decreases, shown by this vertical line, we have at this point the nucleation occurring. The alpha phase starts to form, this is representing the crystallites of the alpha phase. As the temperature continues to decrease, the solid phase now uses up all the liquid, and when we cross the solidus line and come into this alpha region, we have now a polycrystal solid solution, these being the grain boundaries that we had discussed in the previous lectures. So, we have 2 things that we have to remember in binary phase diagrams. First is that there is a tie line for each temperature which defines what would be the composition of the solid phase and what would be the composition of the liquid phase. Secondly, we have the solidification occurring over a range of temperatures, and later on we will see that this defines how the microstructure forms. As this solidification is occurring over a range of temperatures, we find that different types of microstructure can form depending on which regions are crossed during the solidification process. So, in the case of an alloy of copper and nickel, this is an alloy where we have complete solubility in both the liquid phase and the solid phase of copper and nickel in each other. This is because both these elements, copper and nickel, have the same FCC crystal structure. They also have the same atomic radius and valency. So, the distortion of the lattice structure is not much when one of these elements is dissolved in the other. So, what we see below is the phase diagram for copper and nickel. The top region is the liquid phase region, the bottom region is the alpha solid phase region, and as we said before, between the single phase regions we should have a double phase 2 phase region, that is this, where the liquid melt can coexist with the alpha solid phase. We also see now that as temperature drops, say we take a certain composition around 38% nickel and the rest being copper, and if now the temperature of the melt drops, we will see that we reach the liquidus line for this particular composition at around 1280 degrees Celsius. So, that is where now nucleation will start. Alpha phase starts crystallizing as the temperature continues to drop, and this crystallization or solidification completes at a temperature where we meet the solidus line at 1240 degrees. The other things that we see here is that now the melting point will depend on the composition. If we have pure copper, the melting point of the solid is 1085 degrees. If it is pure nickel, it is 1455 degrees. In between, depending on the composition, we will see different melting points for the alloys that form with different compositions. So, some of the things that we have seen are the liquidus line or the liquidus temperature is that at which the first solid begins to form during solidification. Nucleation starts, but does not finish immediately. The solidus temperature or the solidus line is below which all the liquid has completely solidified. These two bound the two phase region which has the liquid phase and the solid phase in equilibrium with each other. We also saw that the melting temperature of the alloy depends on the composition. Now, let us see the phase diagram of aluminum oxide and chromium oxide. We will use this to illustrate how the tie line defines the composition of the liquid and the solid phases, and also tells us about how much would be the liquid phase within the material. So, we have now L defining the liquid phase region. Here we have the solid phase consisting of the oxides of aluminum and chromium, and between these two we have the two phase region, which shows us the region where the liquid phase and the solid phase can coexist. And as we said before, for any particular temperature here given as T close to about 2100 degrees, if we draw a tie line at this temperature, this point where the tie line meets the liquidus line, if we drop it down, we get the composition of the liquid phase denoted as C sub L here. Now, the other end of the tie line, when it meets the solidus line, when we drop it down, we get the composition of the solid phase. Now, this holds good for any composition of the alloy in this region. Say we have a composition C0 defining the amount of chromium oxide in the aluminum oxide. Independent of this, the composition of the liquid phase and the solid phase are always given by this tie line intersection with this liquidus and solidus line. Using this, we can find out what is the percentage of liquid. So, if we take an alloy with C0 percentage of chromium oxide in aluminum oxide, at a particular temperature T, we draw this tie line. The liquid composition is given by Cl, the solid composition by Cs percentage. The percentage liquid is then given by this equation, 100 times Cs minus C0, this part of the tie line, divided by the entire tie line length, Cs minus Cl. So, this will give us the percentage of liquid that is there in this material at this particular temperature T. So, here we find that the values of the tie line as well as the composition intervene. Now, let us see how the binary phase diagram tells us that the microstructure develops. So, we look at how microstructure develops under slow cooling, where crystallization is allowed to occur and the structure to form without any rapid cooling. We look at the copper nickel alloy phase diagram, and if you remember, we said that in the case of copper and nickel, we have complete solubility in both the liquid and solid phases, and we take now part of the phase diagram with a range of about 20 to 55% nickel. This top region is the liquid phase region. Here at the bottom we have the alpha solid phase region. So, let us take the case of an alloy with 35% nickel 65% copper, and we have a melt, and we see how the microstructure develops in this case when the temperature keeps dropping very slowly. So, in the liquid we have the microstructure with uniform mixing of the liquid nickel and the liquid copper. So, we would have a composition with 35% nickel corresponding to that of the alloy, that say is the microstructure at this point A. Now, we decrease the temperature until we meet the liquidus line denoted by point B. Here now nucleation occurs. At this point the composition of the liquid will be that of the intersection of the tie line and the liquidus line, that is 35% nickel. So, the liquid has 35% nickel. To know what is the composition of the nuclei that is forming, we have to draw a tie line, and we reach this point corresponding to 46% nickel. So, the nuclei that form at this particular point will have 46% nickel and 54% copper. Now, the temperature drops further, again slowly we reach say this point denoted by C, and to find out how the microstructure is developed when this point is reached, we draw another tie line. On the left we have the tie line meeting the liquidus line at a liquid composition of 32% nickel, and on the right we have the tie line meeting the solidus line at a point corresponding to 43% nickel. So, that means the liquid at this temperature has 32% nickel, the solid phase has 43% nickel. Okay. So, we find that both the liquid and solid phase have decreased in their nickel content from point B to point C. We drop the temperature further and we go down to the point D, where now we have the right end of the tie line corresponding with the solidus line at a value of 35% nickel. So, that will be the solid content. So, the solid part now has 35% nickel corresponding to this point, and the liquid has 24% nickel. So, this microstructure now looks like this, with the liquid part having 24% nickel and the solid part having 35% nickel. As the temperature drops, we cross over to the single phase solid region. Here now we have a polycrystalline solid with grain boundaries between the different crystals, and you have a completely solid material with 35% nickel in the alpha phase. So, what we saw is solidification occurs in the solid liquid phase region gradually upon cooling below the liquidus line. The composition of the solid and liquid change gradually during cooling. The nuclei of the solid phase form just when the liquidus line is crossed, and when the solidus line is crossed, all the liquid is consumed. Let us see what happens when we have a substance that is completely soluble in another as a liquid, but the two substances are totally insoluble as solids. That would be the case of the mixture of ice and salt, say sodium chloride. So, what we find is that there is a region where we have a solution of water and salt, this is this region. This region both ice and a solution of water and sodium chloride can exist. In this region we have more of salt with the salt water solution, and below minus 23 degrees we have the two solids separate, ice and salt separate below minus 23 degrees. What we find is that for small quantities of salt mixed in water, we have a temperature range say minus 4 to minus 23 degrees, where ice and the salt solution coexist. So, this means that if we take ice and mix a small quantity of salt, that there will be some melting of the ice and a formation of a salt solution below minus 4 degrees. Above this line, the liquidus line, we will have a complete solution forming. So, what we have said is ice and solution for a small quantity of salt being mixed with ice are in equilibrium between minus 4 and 23 degrees. So, when a small amount of salt is mixed with ice in this range, the ice begins to melt and a slush, a mixture of ice and salt solution is formed. This is the reason why salt is used to melt the ice on icy roads. The water freezes and becomes ice, and to melt this ice some small amount of salt is sprinkled, and this salt now has to create a situation where we have some solution form to be in equilibrium with the ice, and the ice melts and the roads become safer for traveling. We can also have alloys with limited solubility. These are called eutectic systems, like in the case of copper and silver. And here we have three single phase regions. We have the liquid phase here over this region. We have a alpha solid phase over this region, a beta solid phase here within this region. Here we have a two phase solid region, that is we have the alpha phase and the beta phase coexisting over this region. So, this means that copper and silver are not completely soluble in the solid phase. Between these different regions we have the alpha plus L region, that means we have a solid alpha phase coexisting with the liquid phase in this region, and then we have the beta, the solid phase coexisting here in the liquid region. This is the liquidus line that we saw before, this is the solidus line, also we saw this before. Now, what we see is there is also another line called the solvus line, separating the region where we have complete solubility and incomplete solubility in both extremes. So, this is the solvus line, and here we have another solvus line. So, again this is the phase diagram of copper and silver. We see here on the x axis pure copper on this end, and with the introduction of silver we have different alloys that can form, and here you would have the case of 100% silver. This is 100% silver. Here we have a region with alpha being the only solid phase, beta here being the only solid phase. This region there is a mix of the two solid phases alpha and beta. So, we saw alpha, which is a solid solution of silver and copper, beta which is a solid solution of copper and silver, and the liquid. These are the three single phase regions. Then we have three two phase regions, alpha plus L, beta plus L and alpha plus beta. We saw that the solvers lines separate the solid solution in alpha and beta respectively from a mixture of solid solutions. This gives the limit of solubility. The solvers lines give the limits of solubility of copper and silver. Similarly, we can see the diagram, the phase diagram for lead and tin. This is also a eutectic system. So, we have here the phase alpha, where we have complete solubility of tin in lead. This is a lead rich solid phase. Then we have beta, which is again a single phase region with more tin than lead. Here we have two solid phases coexisting with each other, again the alpha and beta. This is the solvous line now, this is the liquidous line, and this is the solidus line. This temperature below which the material exists as a two phase solid is called the eutectic isotherm. This defines the temperature below which the solids exist in two phases, and this point where the liquid completely changes into a solid without passing through an equilibrium region with both the solid and liquid is called the invariant or eutectic point. So, we have the three two phase regions, these three two phase regions separated by a line corresponding to the eutectic temperature, and the eutectic point gives the composition that remains liquid until the eutectic temperature. So, you have a liquid which remains liquid until this point and then becomes a solid after crossing the eutectic isotherm or when the temperature is below this particular point. And this also happens only for a certain composition, in this case say about 62% of tin in lead. Now, as the composition changes, the microstructure also will change. Let us take the case of a lead rich alloy, that is very little tin, tin percentage less than say about 2%. So, you will have a melt here with that particular composition. In point A, you have a complete liquid phase. As the temperature drops, we hit the liquidus line, nucleation starts and the alpha phase starts to form. As we go down into this alpha region, now we find that crystallization completes. As in the previous cases, we will have a polycrystalline material with different alpha crystals or alpha grains. Now, let us see what happens when we have again an alloy rich in lead, but with a slightly higher percentage of tin in the range of 2 to 15%. So, instead of the composition being here, now we are looking at a composition in this range. So, we will see what happens when we go down this x bar vertical line, showing how the melt changes into a solid as the temperature is slowly dropped. So, we are first at this point D, which is a liquid solution of lead and tin. We have a certain percentage of tin in this alloy. We now cross the liquidus line and go into the two phase region of alpha plus L. Alpha starts crystallizing, nucleation and crystallization start to occur, and we have now a material which is partially liquid and partially solid at this point E, and we will have to use the same concept of tie line to find out what is the composition of the liquid phase and the solid phase. Now, as we decrease the temperature, we cross the solidus line and we go into this region where we have a single phase solid region. So, at this point F, at this temperature corresponding to F, we will have a solid, a polycrystalline solid with different alpha grains making up the microstructure. As the temperature is cooled further, we cross the solvus line. Now, the solvus line divides the region with complete and incomplete solubility, and as we cross this line, now we go into a region where both alpha and beta coexist. So, the beta phase starts to form within the alpha phase, that is represented here. These red lines show the formation of the beta phase within the gray alpha phase regions. So, you see here that as we go through the different regions, the microstructure changes. We saw previously in the case of lead rich alloy with very little tin, we had a microstructure such as this, where we had only the alpha phase. But now with a higher tin content, as we cross through these regions, as we go into the alpha plus beta region, we have the microstructure changing from this to this. Here we had only the alpha phase, and now we have a beta phase inside the alpha crystals forming. So, at higher tin contents, the beta phase nucleates as the alpha solid solubility is exceeded. We cross the solvus line. So, that means we have exceeded the solubility of tin in lead, and the beta phase forms within the alpha phase. Now, let us see what happens in the eutectic point. So, we take a composition with about 62% tin, that corresponds to the eutectic composition. So, we would have a liquid here, say in this region, for example, at H, at this point H, at the temperature corresponding to H, we will have a liquid with 61.9% tin. Now, we cool this liquid slowly, and what we will see is at this point I, the liquid changes into solid without passing through any phase where the solid and liquid coexist. And we have a structure that is formed like this, called the eutectic structure, where we have layers of alpha and beta phases. Alpha and beta phases have different compositions given by the tie line. So, here if we want to know what would be the composition of the alpha phase, we take this as the tie line, and we go to this point and we see that the alpha phase will have 18.3% tin. On the other side, we see that the beta phase will have 97.8% tin. So, this is tin rich beta phase, and we have a lead rich alpha phase forming as layers. And what we will also see is that as the temperature drops further, this composition will change, because if we were going to draw a tie line here, we will see that in the alpha phase there will be less tin, it will become richer in lead, the alpha phase will become richer in lead. So, in the eutectic region, as the temperature drops further, we will see a change in the alpha and beta compositions. When we look closer into the eutectic structure, we find these layers of alpha and beta, and this is how microscope picture will show the different regions. And as the eutectic structure grows, we find that beta phase will become poorer in lead, the lead will go to the alpha phase, which is becoming poorer in tin as the temperature decreases. So, as growth occurs, as the eutectic structure grows, we find a change in the composition of both the alpha and beta phases. This simultaneous formation of the alpha and beta phases results in a layered microstructure which is called the eutectic structure. The dark layers that we saw in this microscope image give the lead rich alpha phase, and the lighter layers are the tin rich beta phase. Now, let us see what happens at a region other than the eutectic point, but within the range of the eutectic isotherm. So, let us take a case of a composition of alloy with about 40% tin, say C4. So, we will have a melt say in the point J. So, at the temperature J, we have a liquid with a complete mix of tin and lead. So, we have a complete liquid phase. Then we cool this melt, cross the liquidus line and go into this region of alpha plus L, and we will have now alpha nucleating and starting to crystallize. And again, if we want to know the composition of alpha and the liquid, we have to go draw a tie line and we will know what is the composition of the alpha phase. Now, as we continue to cool the material, we will have a change in the alpha phase. For example, at this point very close to the eutectic isotherm, we have an alpha phase with about 18.3% tin and a liquid phase with 61% of tin, which will be the other end of the tie line. We cool further and now we cross the eutectic isotherm, and what we see is outside these grains of alpha we have a eutectic structure formed. This primary alpha which formed in this region will have a tin content of 18.3%, but outside we now have an alpha and beta phase mixed together in the eutectic structure. In this case, the eutectic alpha has an 18.3% tin given by this point, and the beta phase of the eutectic structure has 97.8% tin corresponding to this point. So, we have a microstructure like this where we have the primary alpha phase, these are the primary alpha phases, and then we have a eutectic structure around. So, the primary alpha phase is formed in the alpha plus L region, and the eutectic structure, which is the layers of alpha and beta phases, is formed upon crossing the isotherm. Now, we had looked at binary phase diagrams. We will just spend a few minutes on ternary systems, and before that we have to understand how to read the ternary diagram. So, in a ternary diagram we have three components, say A, B and C, and we draw a chart with the percentages represented in a triangular form where the scale is like this. Suppose we have to mark a point with a certain percentage of A in the composition, we look at the scale going from 0 to 100 along a line perpendicular to the base opposite this point A, which correspond to 100% A. Similarly, for B, if we want to know what is the percentage of B in the material, we look at this line perpendicular to the base opposite to the apex corresponding to 100% B, and so on with C. So, to illustrate, we have marked 4 points. We want to know what is the composition at point 1. We start by seeing how much would be the percentage of A. So, we go to the base opposite to the apex corresponding to A, and we see what would be the composition. This would be 0% A, 10, 20, 30, 40, 50, 60%. So, this point has 60% of A in its composition. In terms of B, again we go to the opposite side, 0, 10, 20% B. For C, we again start here, 0, 10, 20% C. Now, what you can do is look at this diagram and see if you can find out what the compositions of 2, 3 and 4 are. What you will see is that the composition has to add up to 100%, otherwise your result is wrong, and you can do this exercise for now 2, 3 and 4 or any other point to check if you are able to read a ternary diagram properly. So, I hope you have done the checks and you have got the results that are given below for 2, 3 and 4. So, the ternary diagram is used to demarcate materials with different properties. For example, in this system where we have the oxides of calcium, aluminum and silica, we see that different regions have different properties and have been denoted as such. So, at these apexes we have A here aluminum oxide, B which is silica and C calcium oxide. So, we have different regions. For example, this region is the C3S region, which is the tricalcium silicate of cement. This would be completely lime calcium oxide. We have C2S, which is again a compound of cement, and so on. So, each of these regions have different properties and we use these like contours to demarcate different properties. So, as opposed to the binary phase diagram which had temperature on the y axis and composition on the x axis, here we have only composition represented in the ternary system, and we have the ternary system being used to demarcate different regions corresponding to different properties. We have a similar phase diagram which is used for the iron chromium nickel system, where again we have now percentage of nickel, chromium and iron put together to denote different materials and so on. We will complete this lecture with a short discussion of sintering. We already saw that sintering occurs due to diffusion of atoms and molecules between particles when these particles are in close contact and are heated. Now, we should remember that we are below the melting point, we are not heating to above the melting point. However, there is a diffusion of particles and a solid bridge or neck is formed, and this is called sintering. Here the atoms diffuse to the point of contacts, create bridges and therefore reduce also the pore size. The pores between the particles are reduced because of this necking and sintering occurring. This is an example from Young, where we see particles of barium magnesium tantalate BMT sintering and forming a compact structure of particles as seen here. These are particles of BMT with temperature and pressure. A compact structure forms in this ceramic, this BMT ceramic, after compaction and sintering. We also see that sintering will involve grain growth. So, the microstructure changes in sintering. This is because there is a gradual adsorption of small particles into larger ones, and this fills up the grain boundaries. The surface defect now is removed and we have a continuous solid. So, grain growth occurs when there is a movement of grain boundaries by diffusion. If you remember, when we discussed grain boundaries, we said that grain boundaries are regions of high defects and there the energy is higher. And when we go back to the concept of the Condon-Morse diagram, we discussed and understood that we want to decrease the energy, we want to minimize the potential energy or the lattice energy in order to have a stable microstructure. Therefore, this diffusion in sintering tends to do away with some of the grain boundaries and the grains grow in size. So, if you have an initial microstructure with small grains or less than 5 microns, say 2-3 microns, with some temperature and pressure, there is diffusion across these grain boundaries and the grain boundaries fill up to have finally a structure with larger grains, say in the order of 10 microns. So, the grain sizes and the microstructure changes due to diffusion during sintering, and this is a picture of alumina ceramic seen in SEM micrographs. You see here before sintering how the grains are smaller grains, and after the application of temperature and pressure we have the same ceramic now with larger grains. This concept is also used for bonding different pieces. This is called diffusion bonding, which is a joining technique in which two surfaces are pressed together at high pressure and temperature, which causes them to bond to each other. Say we have these two elements which are put together and forced together, small application of force and temperature, and now diffusion occurs across these grain boundaries and the material joins. So, the different steps are: initially you have a contact area that is small as these two elements are put together, pressure is applied, this deforms this surface and causes more area to be in contact, this increases the bonding area. Then there is diffusion across the adjacent grains, the adjacent grains start bonding, you have growth in the grain sizes, the voids tend to shrink because we have diffusion and filling up of these voids. With further diffusion, these voids can also get filled up. So, we have covered different ways that microstructure forms in different materials. We looked at phase diagrams of single component systems, two component systems or binary phase diagrams, and we also saw how we can use a ternary diagram, and finally we saw how grain structures can change due to sintering brought about by the diffusion process. Thank you very much. We have some questions regarding the lecture on the development of microstructure that we will take up now.
Sir, how diffusion is related to defects?
Well, that is a good question. The movement of atoms due to diffusion is governed a lot by defects. Early in this lecture or the previous lecture, we looked at how diffusion is faster along some areas of defects. So, if you have a grain boundary, there is a region where the structure is not very compact and therefore, the diffusion is very fast through the grain boundaries. And also we found that in the core of a dislocation, the movement of atoms through diffusion is also faster. So, defects clearly affect, and generally when we have a defect, we have faster diffusion through the defects than in the bulk of the material. Now, also what we saw in this lecture towards the end is that when there is diffusion, the defected area tends to be filled up by the atoms. Therefore, grain boundaries also disappear. You have the small grains becoming larger because the grain boundaries are filled up by atoms or particles when there is diffusion during sintering. So, there is a lot of interaction between defects and the diffusion. First of all, diffusion is faster in defected areas, and diffusion can also lead to filling up of the defects, and you have the elimination of grain boundaries. You had the question on
Okay, so sir, can you explain some applications of sintering in civil engineering structures or civil engineering materials?
Yeah, lot of ceramics, the microstructure of ceramics forms by sintering. If you have bricks, if you see the case of bricks, there is sintering bricks, and lot of the examples that I showed are ceramics, structural ceramics, which are powders that are pressed together with some amount of temperature, and these grains now bond to each other and become larger, and you have a sintered structure, and this could also be used to create aggregates and to create the ceramics that we use in engineering. Okay, thank you.